In this video, we're tackling the design of a real-time chat system. Think of something like WhatsApp, WeChat, or Facebook Messenger. These systems are deceptively simple on the surface. Send a message, receive a message, maybe get a notification. But under the hood, they require careful engineering to support real-time delivery, high availability, multi-device sync, group messaging, and message durability, all while keeping latency low and data secure. Our goal is to explore how we'd architect such a system end-to-end, including the key components, message flow, and deep dives into real-world concerns like service discovery, presence management, and device synchronization. Let's dive in. The problem is to design an instant messaging system like WhatsApp or WeChat or Facebook Messenger. Here are some good requirement questions to ask. Shall we support both one-on-one and group-based? What's the DAU? Is there a message size limit? How long shall we store the chat history? Is it text only? In this slide, we walk through the high-level architecture of a real-time chat system. Client connections. Each client connects to a chat service, which acts as the backbone for sending and receiving messages. These connections are maintained using WebSocket, a protocol that allows for bidirectional, persistent connections. This ensures low latency and real-time communication between clients. Chat servers. These servers are responsible for handling the core messaging logic, sending messages from one client to another, managing delivery acknowledgements, and queuing messages if recipients are temporarily offline. Presence servers. Presence is a key part of a chat experience. These servers track which users are currently online or offline. This information is used for features like last seen or real-time availability indicators. API servers. All traditional RESTful interactions, such as user logins, signups, and profile management, are handled here. These servers also support non-real-time operations and management features. Notification servers. These servers handle push notifications for message alerts, especially when the app is closed or in the background. They integrate with mobile push services and email SMS gateways when needed. Key value store for chat history. To ensure fast retrieval, especially for recent messages, chat history is stored in a key value store. This is optimized for speed and typically backed by persistent storage for long-term reliability. Data models. For one-to-one messaging, we use a simple table with columns like message ID, from, to, content, and created at. This captures all necessary metadata and enables efficient querying. For group chats, we need a more scalable model. Here, messages are associated with a channel ID and also store the user ID of the sender, the message ID, content, and created at. This structure supports features like channel history and per-user permissions. This modular, service-oriented design ensures the system is scalable, fault-tolerant, and provides a smooth, real-time user experience. Let's now take a deeper look into the architecture of our chat system by walking through some of the critical components and workflows. Service discovery. When a user connects, we need to recommend the best chat server, ideally one that is geographically close and not overloaded. This is where tools like Zookeeper come in. They help us maintain a dynamic registry of available servers and their metadata so we can intelligently route clients. One-on-one chat flow. Suppose user A sends a message. The chat server they're connected to, let's say server 1, generates a unique message ID via the ID generator. The message is persisted to a key value store and pushed to a message sync queue. If user B is online, the message is delivered to the server they're connected to, server 2. If B is offline, a push notification is sent via the notification servers. Server 2 then forwards the message to B through an established WebSocket connection. Group chat flow. For group chats, each member has a personal message sync queue. When someone sends a group message, it gets copied to every member's queue. However, this model doesn't scale for large groups. In those cases, we optimize storage by storing a single message and referencing it for all users. Device synchronization. A user may be logged in on multiple devices. Each device maintains its own max message.id. When a new message is received, the server compares this value with the message ID in the store to determine if the message is new for that device. This helps synchronize across devices efficiently. Online presence. When users connect via WebSocket, their online status and last active timestamp are saved in a KV store. However, due to frequent disconnects, we use a heartbeat mechanism to confirm active sessions. If a heartbeat isn't received within a time window, the user is marked offline. When status changes, it's fanned out to relevant contacts via pub/sub channels. Message optimization. Messages can be compressed before sending to reduce latency and bandwidth. For media-heavy content, we use cloud storage and just share URLs. We implement end-to-end encryption to protect message privacy. This means only the sender and recipient can decrypt the messages. Clients cache messages locally for faster access. Lastly, we have a message resend mechanism to handle failures. If a message isn't acknowledged, it is queued and retried. This deep dive highlights how we ensure reliability, scalability, and real-time performance while keeping user experience and security at the forefront.